Okay, the next quantum mechanical system or model that we consider is known as the particle in a box system. And this is used when we confine a particle. So basically what we have in this system is a specific particle with mass m, and it's confined to what we call a one-dimensional box, which is basically a line. So we're only going to look at the one-dimensional system in detail. So this particle lifts on a one-dimensional line, and it is confined between two walls at x equal to 0 and x equal to L. So we can describe the system or draw a picture of the system in the following way. There we have the x-axis where the particle lifts, and there we have the two walls. One wall starting at x equal to 0 and the other one starting at x equal to L. Inside this box, which is this region where the particle can move, the potential energy is equal to 0. And inside the two walls, the potential energy is infinity. Okay, so this basically describes the system that we're looking at, which is also illustrated in this picture. Now, this specific model can be used in chemistry, for example, to describe a gas molecule, a single gas molecule in a one-dimensional container. Okay, now let's look at the quantum mechanical description of this type of model. Oh yes, it can also be used as a description of conjugated molecules, and this is what you use in experiment 5 for the methyl red molecule. So if we consider this region inside the container where the particle can move, we basically have the same system as a freely moving particle that we've already considered. So we already have the Schrödinger equation, because it's the same as that for a free particle. And we already have the equations for those, or the two solutions to the Schrödinger equation. Okay, so we have the solution to the Schrödinger equation, both in terms of wave function and kinetic energy for that region. But one can now write the wave function expression a little bit differently by using the Euler relationship. So if you take that wave function expression and write a e to the ikx, and you take the e to the ikx term and write it as cos kx plus I sin kx, and you do the same for b to the minus ikx, you can write the equation in the following way. So basically you have the cos terms together and the sine terms together. But these are constants, and I together with I minus b, these are also constants. So let's replace that with a constant d and that with a constant c. So basically what you have is the wave function is c times sine kx plus d times cos kx. And the energy expression remains the same. And remember, we said if you have a freely moving particle, any value for the energy is acceptable. Okay, so basically we've done all of this already. However, things are a little bit different in the case of the particle in a box, because the particle is now confined, and as a result of that, not all values of energy are permitted, because we'll see in a moment that there are certain boundary conditions. And the reason for this is if you have a confined particle where you have potential energy going to infinity, the wave function basically goes to 0 where the potential energy is infinite. So your wave function in this case, where x goes to 0 and x goes to L, has to go to 0. So whatever your wave function looks like inside the box, here at x equal to 0, where the potential energy goes to infinity, the wave function has to go to 0. So these are our two boundary conditions. And if we express them mathematically, every wave function with our counter k at x equal to 0, so that indicates x, must be 0. And every wave function at x equal to L, which is that region or that point, must go to 0. So this is an expression of the boundary conditions. And the moment we introduce these boundary conditions, as you'll see in a moment, we will get quantization. So for the freely moving particle, there's no quantization, but for the confined particle, we start to see quantization. Okay, so let's derive the equation for the energy levels as well as the wave functions for the particle in a one-dimensional system. And in deriving the energy level equation, we will also show that the system is in fact quantized, or the energies are quantized. This you need to know as a proof for the test and the exams. Okay, so what we're going to do, we're going to prove firstly the quantization of energy, and then secondly derive the wave functions for the particle in the 1D box system. Okay, for the A part, we're going to use standing waves. And we're going to assume that these waves must fit into the box. So we're going to consider each wave function to be a de Broglie wave that must fit inside the 1D box. Okay, now what does a standing wave look like? If this is the box, that's x equal to 0, x equal to L, and let's just extend the box to 2L. This is one type of wave that can fit inside the box. And in this case, the wavelength is equal to 2L, because then the wave repeats itself. Another option is to take the box and do that. And in this case, the wavelength is 1L, so one wave fits inside the box. And these are examples of standing waves. Another option is to fit one wave in 2/3 of the box. So there's 1/3, 2/3, that's one box. So in that case, the wavelength is 2/3 of the box. So if you were to express this wavelength of the standing wave, one can say for a standing wave, the wavelength can be expressed as 2L divided by something. In that case, that something is 1. In that case, that something is 2, because 2L divided by 2 is 1. In that case, that something is 3. And let's call that something n. So 2 divided by 1 is 2L, 2L divided by 2 is 1L, and 2L divided by 3 is 2/3L. So this is a general expression for the wavelengths of the standing waves that we can fit inside a box of length L. So remember, the length of the box is L. And in this case, our N is 1, 2, 3, etc. Okay, so we now have the wavelength of the standing waves that can fit inside the box. And obviously the waves have to fit inside the box for the particle described by the waves to be in the box. Now we're going to use that equation, remember this wavelength equation, because we have another equation that describes wavelength. And we said these are de Broglie waves, and we have the expression for the wavelength according to the de Broglie equation. And we now also have this expression that we've just derived. So from the de Broglie equation we can say that linear momentum is h divided by lambda, and if we now substitute that equation, it becomes nh over 2L. So using that wavelength expression there. Okay. So we have an expression for linear momentum from the de Broglie equation in terms of the length of the box. Okay, but we also know that the potential energy is 0 inside the box, and the particle only has kinetic energy inside the box. So remember, we want an expression for energies. That's what we want, and we want to show that these energies are quantized. So we have an expression for kinetic energy, but it only has kinetic energy, so the kinetic energy must be the total energy, which is equal to, remember this equation we've derived before. And now we have an expression for linear momentum that we can substitute there in terms of the length of the box. Sorry, there's a 2 missing there. 2, 4 over 8. But because this n is basically the counter that we're working with, we can add an n to the energies. Because depending on what our counter is, if n is 1, 2 or 3, we're going to use a different n. So basically what we've done, we've said because there's only kinetic energy, we have an expression for kinetic energy that we derived right at the beginning. And we have now expressed the linear momentum in terms of the wavelength that we used. In terms of the length of the container, we can now make this substitution and we can get an expression for the energies for the system. So basically our energies equation looks like this. And because we have this value for n, and n cannot take any value, it means that energies are quantized. So we have achieved both our goals. Firstly, we have shown that energies are quantized, and we've also derived the energy equation for the particle in the box system. The B part of the question asks us to derive the wave functions for the particle in a box system, and here we are going to make use of the boundary conditions. Now remember, previously we have obtained this equation in the lecture notes. And this is basically for a freely moving particle. So please go back to your notes if you're not sure where that equation comes from. So this is the same as a freely moving particle. But now we have to apply the boundary conditions. Okay, so let's consider the first wall. At the wall x equal to 0, so at that point. We know that the wave function has to go to 0. So what does the wave function at that point look like? So that is for x equal to 0. So it's c sine kx plus d cos kx. How do I make that wave function go to 0? Well, if x is 0, sine of 0 is already 0. So that part is okay. So this term is problematic. How do I make that term go away? Well, I can make that term go away by making d equal to 0. So that is what I'm going to do. Why don't I make c equal to 0? Well, basically because sine of 0 is already 0. So I don't have to take care of that term. But the reason is, but cos of 0 is 1, so I have to get rid of that. Thus, I make d equal to 0. So what does the wave function look like then? The wave function basically then becomes, c sine kx. So that second term falls away. Now let's look at the second wall. So at x equal to L, which is there. At that point the wave function also needs to go to 0. So the wave function at point L at this stage is c sine kl. So I've just replaced the x with an L because I'm working at the point x equal to L. So that must also be 0. So how do I get this to go to 0? One option is to make c equal to 0. But what will happen to the wave function then? The wave function will be 0 everywhere, and I can't allow that. So if we make c equal to 0, then the wave function will be 0 everywhere. And that is not acceptable. If you think back to our requirements for wave functions, the wave function cannot be 0 everywhere. But if you think back to the shape of the sine function, and we have discussed this before, the sine function is 0 at values of pi, 2 pi, etc. So if we choose, so our wave function looks like this at the moment. So if we choose this KL such that sine KL is equal to 0, then we are fine. And how do we make sure that that happens? Well, at each n pi, so 1 pi, 2 pi, 3 pi, 4 pi, etc., the sine function goes through 0. So if this x is equal to n pi, then this function, the wave function, will be 0. We can also express that as k being equal to n pi over L. So if that is true, this will be 0. Just be careful, we cannot make n equal to 0, because in that case you will have sine of 0, which is always 0. Then the wave function will be 0 everywhere. So n equal to 0 not allowed, because then the wave function is 0 everywhere. Okay, so what does our wave function look like now? But now I'm expressing the wave function in terms of n. And I'm replacing KL, sorry, it was Kx initially. I'm replacing K with n pi over L x. So this is the general wave function of the particle in a box. And our n runs from 1, 2, 3, 4, because at 1 pi, 2, 1 n pi, 2 n pi, 3 n pi, etc., the sine function becomes 0. So this is the expression of the wave function for the particle in a box system. Okay, so we've just derived the wave function as well as the energy equation for the particle in a box system. And what we've seen is that because boundary conditions are applicable, only certain wave functions and certain energies are acceptable in the case of a particle in a box, as opposed to the freely moving particles where any energy level and any wave function is acceptable. Okay, so at this stage we have the wave function for a particle in a box looking like this. And there's one more thing that we need to do to this wave function, and that is to normalize the wave function. And that basically entails finding this normalization constant C. Remember, this ensures that all the probabilities add up to 1. So let's look at finding the normalization constant. Now remember, we're integrating over all the probabilities, so the square of the wave function, and we have to consider the space available to the particle. Now the particle is confined in the box, so the space available ranges from x equal to 0 to x equal to 1, and that integral must be equal to 1. That is how we defined the normalization constant. If you're not sure about how we define this, please go back and have a look at your notes. Okay, so now we're going to normalize the particle in a 1D box wave function. So normalizing that wave function, finding C. Okay, so to normalize a wave function, we basically have to find that, ensure that the probabilities add up to 1. In this case, our wave function looks like that. We have the square of the wave function here. We don't have an I in the wave function, so the complex conjugate doesn't really make a difference. So the square of the wave function looks like that. So the integral that we want is this integral. We're integrating over the area, the area that the particle occupies. And we make that equal to 1, and we find C. So this is the approach that we're taking. So if you look at this integral, we now have to find this in the data sheet. And we have a sine squared of something, x dx. But if you consider this, remember, all of these are constants. X is your variable, the thing that you integrate to dx. Pi is a constant, L is the length of the box, that's a constant, and n is just a counter, that's also a constant. So effectively you can see this as a constant a or k or whatever. So the integral that we're looking for is sine squared constant x dx. That's also just a constant, so you can take that to the outside of the bracket. So if you have a look at your data sheet, you will notice at the bottom of page 2 there is an integral that says sine squared ax dx is equal to x over 2 sine 2ax over 4a. So this is the one that we're looking for. Why? Because we have a sine squared ax. Sine squared ax. That one won't work because that's not a squared. The others are also not applicable. There is a sine squared x dx, but that one doesn't have an a. It doesn't have a constant in front. We need the one that has the constant in front, because we don't just have an x there, we've got an ax. We've got a constant in front of the x. So that is the integral that we're going to use. So if we carry on using that, so we can say from the data sheet that is equal to half x minus 1 over 4a plus 2ax. So in this case, our a is equal to n pi over L. So everything except the x is the a. Okay. So let's go to the integral. Okay, so now we have to keep our bearings. So the c squared, you can just take outside the integral, and that becomes half x minus 1 over 4. Our a is n pi over L sine 2 n pi over L is a, and then you have a x, and this runs between L and 0. Okay, now we make the substitutions. C squared. Firstly, we replace x with L. So that becomes L over 2. Remember, x is, let me just write it there, x is on top of the line. L over 2 minus 1 over 4 n pi L sine of 2 n pi, x becomes L over L, minus 0 over 2 minus sine of 2 n pi 0 over L, and all of that is divided by 4 n pi over L, minus, no, sorry, that's fine. Okay, and then we close the brackets. So here we have c squared L over 2. What happens to that term? The L's cancel, and sine of n pi, or 2 n pi, or 3 n pi, or 4 n pi is always 0. So that whole term becomes 0. That becomes a 0, plus times that becomes a plus, and sine of 0 again becomes 0. So all of these terms fall away. So what you're left with is c squared L over 2. and that must be equal to 1, because we said the integral is equal to 1. But what are we looking for? We're looking for c. So c squared L is equal to 2. C squared is 2 over L. C is 2 over L to the power half. Okay, so that is our normalization constant. So if we were to write out the full normalized wave function, instead of c, we write the normalization constant and this is for x between 0 and L. So there we have the normalized wave function for the particle in a 1D box system after we have determined the normalization constant.